One of the students has asked me a question from the textbook, exercise 10.6, question number 15. Now, this is a really very nice question because it combines both compound interest and annuities in one question. Ivan made equal deposits at the end of every month for 5 years, so he's made 5 years of monthly deposits or 60 deposits into an investment fund. He then left the money in the fund to grow for another 4 years. So he's for another 4 years, the subsequent 4 years, he has not made any more deposits, but it will certainly grow at a compound interest rate. If the fund earned 4% compounded monthly for the entire period and the accumulated amount at the end of the term was $100,000, calculate the size of the periodic deposit. So in order for me to understand what's happening here, I think what I'm going to do is I'm going to draw a time diagram. I always like to analyze the problems by reading them carefully, and I often have to read them twice, and then I will prepare a time diagram to make sure that I fully understand the consequences of all of the parts of what's happening here. So for the first 5 years, Ivan is making deposits, and in that 5-year time period, he makes a total of 5 years of monthly deposits. So he's going to be making a total of 5 times 12, or 60 monthly deposits. We don't know how big these deposits are, so I'll just use the letter R to stand for the regular monthly deposit, or the monthly payment. That's PMT, by the way, on your calculator. So here we have an annuity of N is equal to 60 deposits of our dollars. So at the end of 5 years, he now has a certain amount of money accumulated, but he leaves it in for another 4 years. So the money earns interest, or compound interest, for 4 years, and the interest rate is 4% compounded monthly throughout the 9-year period. So for the full 9-year period, we're looking at an interest rate of 4% compounded monthly. So that means that the rate per month is 4% divided by 12. Now, at the end of 4 years, he has, or after 48 monthly periods, he has accumulated a final value of $100,000. And so the question becomes, how much has he deposited? What is the size of the regular monthly deposit in order that he has $100,000 at the end of the 4-year time period? Now, that 4-year time period means that the number of interest periods is 48 monthly periods. So he's earned compound interest for 48 monthly periods. He's accumulated an annuity for 60 monthly deposits, and so this is obviously going to be a 2-step problem. The first thing that we need to do is to figure out how much he needs to have in his annuity at the end of the 5-year time period. So I'm going to set my initial focal date to the 5-year time period. So there's my focal date, FD. So label your focal date. So I'm going to say, what is step 1? Step 1 is to find out how much is in the account at the end of the 5th year. And the way I'm going to do that is I'm going to start off with the $100,000 and discount it. I'm going to discount it over that 4-year time period at the compound interest rate. So step 1 is to find the present value of the $100,000 4 years before he had it. So that's going to be using the formula principal is equal to maturity value times 1 plus I to the negative n. And by the way, I'm going to talk about this problem using both the financial calculator solution and the algebraic solution, but I'm going to start with the algebraic solution. So that principal will be equal to the $100,000 multiplied by the compound discount factor of 1 plus 0.04, 4% per month for 12, divide that by 12 periods per year, so 4% divided by 12, and that would be raised to the power of negative 48, because there's 48 monthly periods that within which I have to discount it. And you will get a principal value that whatever that number is, what I want you to do now is I would like you to, by the way, that principal value works out to be a value of, I think it was 237.0, and whatever it is, I want you to store it in memory 1. I don't care. Just put it somewhere, but store it in memory 1. So that's the amount of money, $85,237 and some pennies, stored in memory 1. That's the value that is the value of his deposit at year 5. And now we are ready to take that amount now and work that amount at year 5 to determine the size of the monthly deposit. So that's going to be step 2. So step 2 is to determine the payment or the size of the payment using the $85,000 number, the $85,237 and 06 cents, whatever that is. If you look back at the time diagram, you'll see it's at the final value of all of the deposits. So now that present value becomes the future value of the deposit. So I'm going to say that this is equal to the final value of the 60 deposits. So now we're going to use the other formula, the future value formula for annuities. So we're going to have 85,237 and 06 is equal to whatever your payment size is multiplied by the annuity formula, the final value factor for annuities. That would be 1 plus 0.04 divided by 12. How many deposits are there? Well, there are 60 of them, and I have positive 60 because I'm looking at the future value formula, minus the 1 divided by the interest rate per period, and that would be 0.04 divided by 12. Be very careful with your brackets and so on in the order of operations when you're working this out on your calculator. Remember that this is per month, and so this interest rate that's in here must be per month as well, just like that must equal to number of monthly deposits. They all have to coincide. They can't conflict. They all have to occur with the same frequency. Solving this for the payment, it works out to be a monthly payment, I think of $12.85 and 65 cents per month. So his monthly deposit must be $1,285.65 per month for the 5-year time period. So now the question becomes, how do you do this problem using the built-in function on your calculators? So going back to the time diagram, we still have the same time diagram. We've got 48 interest periods in the last 4 years. We have 60 deposits in the first 5 years, and we've got I/Y is equal to 4. So we're going to start off with IY is equal to 4. Then we go into second IY, and we're going to enter in compounding periods per year is 12 because it's compounded monthly, and payments per year is also equal to 12. Make sure that they are consistent. So we've got payments per year and compounding periods per year. This is the interest rate. That's really, really important. And now you can go second quit to get out. The first thing that you're going to do is you're going to start off with this being the final value. So we're going to key in final value is equal to $100,000. N is equal to 48 because there are 48 interest periods in the last 4-year period. And PMT is equal to 0 because there are no payments in the annuity. And I think that we've entered in all that we need here. What we need to do now is to hit compute the present value. And if you compute the present value from this, you will now get the present value being equal to 85,237 and whatever the number is. I think it'll be 05, and I'm not sure, 059 and so on, whatever it is. It really doesn't matter. Again, I'm going to ask you to store this. And if the future value has been entered in as positive, the present value will be coming out as negative. So remember that there's always going to be a difference in the signs. Each one will be the opposite sign of the other. So it makes no difference which one is positive and which one is negative, as long as you recognize that they will always be the opposite sign. So I'm going to now store this in memory 1, or it really doesn't matter where you store it, but put it in memory 1 or somewhere where you know where it is. And now what you recognize is that this amount of 85,000, 85K, is now going to be represent the future value of the annuity. So now we're ready for step 2, because in step 2, what we're going to do is we're going to take the final value of 85,000 and make that the final value of 85,237.05. So overwrite the previous final value. Now we're going to change the PMT to be equal to, well, we don't know what the PMT is, so I think I better erase that. Okay, better take that out because I don't know what the PMT is. I do know that the present value is equal to 0 because I have nothing in the account at the beginning, so I might as well put that in. The number of payments is equal to 60, and let's see what else is there. We already have the IY, the CY, and the PY in there, so what else do we need? Well, the only thing that we need to do now is to compute, CPT, compute the size of the payment. And of course the size of the payment will be opposite sign to the future value. So if the future value was entered in as positive, your payment will be negative. If your future value was entered in as negative, your payment will be positive. And that payment should work out to be $1,285.65. Okay, 65 cents. Now you know that the payments will never be negative, nor will the future value be negative or positive. They have to be opposite sign though in order for your calculator to work out the values. So the difference between the positives and the negatives is whether it's a circumstance of money going in or money coming out. It depends on what side of the wicket, or the teller's wicket, that you are standing. So there you go, 2 solutions, algebraic and financial calculator. So you can choose which method you like for the purposes of the final exam, whichever method you're comfortable with and whichever method you understand. What works for you?